Hi, my name is Shafiuddin Rehan Ahmed. I'm a final year PhD candidate in Computer Science Department at the University of Colorado Boulder. In this presentation, I will go through the paper Linear Cross-Document Event Coreference Resolution with Cross-Document Abstract Meaning Representation, or X-AMR for short. The presentation is divided into 6 sections, in which first I lay out the main motivations for this work, urging the need for corpus-level event representation as a way of compressing information. Then I will provide details for the X-AMR annotation guidelines and the model in the loop annotation tool. This is followed by experimenting a linear graph-based event coreference resolution algorithm that I introduce in this work that leverages the X-AMR annotations of the enriched event coref bank corpus, the annotations that are provided by human annotators. Then I will continue by using GPT-4 as a replacement for the human annotators in 2 different prompting techniques and show its limitation on this task. I will follow this by discussions on certain qualitative and quantitative analysis, and finally conclude with avenues for future work. Without further ado, let's get started with the main motivation for this work. The first main motivation is the inherent ambiguity in establishing singular terms for event mentions. This deals with the fundamental difficulty in producing unique symbols for events that can be compared for identity. The result of this is that we are forced to use pairwise methods for event coreference that aim at estimating approximate similarities between the mentions. We also are forced to guess what is the right context for an event in this estimation. That is, whether to use the sentence, the segment, or the entire document in which the events appear. The second motivation is to circumvent the quadratic complexity of pairwise methods, coreference methods, with a linear algorithm. The quadratic complexity of the pairwise methods is particularly an issue when using the recent large language models for this task, especially where it is required to use entire documents as context for events. Clearly, these methods do not scale on large corpora. In this paper, I will focus mainly on the research questions. 1. How can we accurately compress information and establish singular terms for events? And B. How can we assess such symbolic representations efficiently with the linear ECR algorithm? The next sections address these 2 research questions through X-AMR. X-AMR is best described by using this example. Here we have 3 event mentions M1, M2, M3 taken from the ECB plus corpus that speak of 3 acquisition events. In these, M1 and M2 are coreferent or identical, and M3 is a similar but different event. Note that for M2 we need extra sentential information for making the coreference or non-coreference decisions between the other 2 mentions. X-AMR quite simply aims at identifying the crucial and sufficient event semantics for making the coreference decisions. In other words, X-AMR aims at circumscribing an event around its minimal participants, that are the event arguments, arg0, the prototypical agent, arg1, the patient or the theme, the location, and time in which the event happened. What differentiates X-AMR from standard AMR is the incorporation of verbnet in resolving synonymy of the role sets for the event triggers, which is a straightforward method of event typing, and the resolution of the arguments at a corpus level through a constantly updated knowledge base. We claim that while the human judgment is ambiguous in directly creating symbols for events, we see that it helps in filling missing information of events in the documents such as location and time, and thus helps in establishing the event identifiers to this resolution. For instance, by generating the X-AMR representations for the 3 events, we are able to match M1 and M2 as they have the exact same graphical representation, and also distinguish M3 from M1 and M2 by comparing the arg1 and the time for the acquisition event. We claim that X-AMR is an efficient way of compressing documents and representing events. Next, we test this claim by running human annotations on the ECP plus corpus, enriching it with the X-AMR annotations for its mentions, and introduce a novel linear ECR algorithm that uses X-AMR to do the coreference. Before I begin talking about the ECR algorithm, it is important to highlight nested events and how we handle them in X-AMR. Nested events are the special events in which either arg0 or arg1 is in itself an event. In this example, If we focus on the agreement event, we observe that the arg1 for this is a proposition, an action in this case of the acquisition of EYP by HP. The way we handle this annotation in our annotation tool is by allowing annotators to mark the role set ID of the arguments, which later expanded in post-processing. We also focus only on the arg1 in the nested structure due to the nature of the ECB plus corpus, which deals mostly with actions. Why we need to take care of nested events? Well, we see that a significant percentage of mention in this corpus are nested events. As mentioned before, we enriched the ECB plus corpus with X-AMR annotations using a user-friendly annotation tool. The annotation tool has a model in the loop that assists the annotator by suggesting the arguments from previously annotated documents. It also has the prop bank interface to look up role sets definitions easily during the annotation. The tool is discussed in more detail in another paper called X-AMR Annotation Tool, which was published recently in the EACL conference in the system demonstration track. We employ two annotators for this annotation task, where we follow a two-step approach in which we first task the annotators to identify the correct role set sense for the event triggers. Then we ask an adjudicator to resolve the senses that the annotators disagreed on. Finally, all the event mentions are annotated with X-AMR using the role set sense definition from prop bank. At the time of writing the paper, we achieved the most comprehensive annotations on the development split of ECB+. Therefore, we use that for our experiments. Remember, the goal of this work is to create unique symbols for events that can be compared for identity. Formally, for any two events Mi and Mj, we say Mi is coreferent to Mj if and only if the event identifiers are the same. The benefits of approaching coreference in this symbolic way is that now instead of comparing every mentioned pair for coreference, we can bucket the same event identifiers to their same event according to their identifiers. The way we generate EIDs vary for standard and nested events. For standard events, we simply generate a tuple of the corpus level arg0, the resolved or unresolved role set ID according to verbnet, and arg1. We also generate another EID using the arg0, the role set information, and the location and time arguments. For nested events, we employ a recursive strategy to generate the EIDs. Specifically, we generate multiple EIDs by traversing the nested arguments up to a certain depth. The goal here is to connect the root event to a standard arg1. Since we generate multiple EIDs, we slightly modify the coreference definition. Now we say Mi and Mj are coreferent if and only if they share one or more common identifier. To illustrate this with an example, consider two nested announcement events of the acquisition of EYP by HP. In M4, the announcement is connected to the acquirement through signing of a document, of an agreement. Following the EID hop generation algorithm, we get two identifiers for M4 and a single identifier for M5, in which the two hop identifier of M4 is exactly same as the identifier of M5. We compare various baseline methods with the usage of EIDs. The standard methods without using EIDs include just using the lemma of the mention trigger for bucketing mentions. To see the benefit of prop bank senses, identifying the prop bank senses, we also try with and without resolving the senses with verbnet. For the methods that use EIDs, we vary our methods by only using EIDN and EIDLT and the combinations of them with the resolution of senses with verbnet. The combination methods include the EID and EIDLT, where every argument needs to be the same to cluster events, and also EIDN or EIDLT, where either the EIDN or EIDLT between the two mentions are to be the same for coreference. Since we have annotations from two annotators, we also employ a combination method that identifiers of A1 or A2, which is to be interpreted as cluster mentions if either A1 or A2 recognize it to be the same between two mentions. Looking at the clustering results, we see the clear benefit of using prop bank when compared to just using the lemma with a 3.6 kernel score improvement. When comparing the role set resolved with verbnet classes, we can say that there is a lot of scope for improvement in the verbnet class annotation. When assessing the EIDs method, we can clearly see the OR clustering method of EID and EID-LT yields the best performance across the annotators. The AND clustering method provides a precise alternative. These results provide an upper bound for purely symbolic method. The most useful outcome of this work is that we provide a method of annotating ECR links for free in a linear way when compared to the traditional way of annotating ECR links, which as we know is very tedious. Jumping topic to now assess how GPT-4 performs in the X-AMR task as a replacement for human annotators. We use GPT-4 as a way of abstractive generation of the X-AMR annotations. We employ two prompting techniques differing in the context provided for the annotations. We first condense the annotation guidelines of X-AMR into a concise set of instructions. The X-AMR annotation task is then converted into structured JSON prediction where we provide the key definition of the JSON in the prompt. The generation is done basically by answering questions such as what is the event trigger, is the event nested, who are the participants of the event, when and where did the event take place. We also task GPT-4 to produce a single sentence description of the event that includes the identified role set and the argument information. In the first method G1, we use the entire document of an event as context to identify the document level AMR of the mentions. Now since G1 has only the document level context, we also employ another technique G2 which effectively uses corpus level information in generation. Instead of passing the document text, in G2 we pass a set of complete events from the topic of the target event mention. Complete events are the ones that have all their arguments are identified. For example, as shown in the figure, this technique helps in identifying the missing location and time information of a target event by incorporating the set of complete events in the prompt. GPT-4's task is to then identify the most suitable complete event in doing the X-AMR annotation in a retrieval augmented generation methodology. Consequently, G2 addresses the limitations of G1 by aggregating information from various documents and not just the document in which the target event appears. We run the clustering baseline methods on the X-AMR graphs produced by G1, G2, and the annotator A1 for a smaller subset of the development set. Note that this set is bounded by recall. The key takeaways from this are as follows. Both GPT methods fall short of the annotators A1 and struggle at even surpassing the clustering method using just the proper exams. Between G1 and G2, we see a significant improvement in G2 over G1 of 10 points in Connell score, hence showing that GPT-4 is able to aggregate the information from complete events in generating better X-AMR graphs. Although the results are subpar, we believe that there is some value provided by GPT-4, especially in the generation of the concise event descriptors. Next, I go through the qualitative and quantitative analysis that we did in this work. To show the linearity of the ECR algorithm, we devise a synthetic experiment in which we make copies of the annotated mentions with X-AMR to scale up the dataset. We plot the line it takes in seconds to run the event identifier generation and the clustering algorithm on this inflated dataset. As shown in the figure, the complexity is roughly linear with a very small area between the reference line and the elapsed time curve. We also run a qualitative error analysis on the smaller subset. The main takeaway from this was that X-AMR provides an intuitive way of analyzing the annotation mistakes, both in the original ECV plus corpus as well as in the X-AMR annotation. To conclude, we introduced a corpus level version of AMR called X-AMR, providing the annotation guidelines, the annotation tool, and the annotations by humans. We introduced a novel graph-based ECR algorithm that serves as an efficient, linear way of doing cross-document coreference resolution. We compared GPT's performance as an annotator for the X-AMR, including a retrieval augmented generation method for aggregating corpus level information in the generation process. The future work mostly revolved around combining the symbolic representations of X-AMR with state-of-the-art BERT-based event coreference methods to filter or to sample mention pairs efficiently. Representation learning and distillation of the event description generated by GPT-4 with smaller in-house LLMs like Llama is another promising avenue for future work. With that, I end my presentation and I'm open for questions if there are any.